Hello everybody, my name is Philip Johnson, and today I will discuss the fourth experiment for our physics course involving energies at play in a spring system. The objective of the experiment was to analyze motion of a spring system and swinging in an arc shape similar to the extreme sports video presented in video lectures for the course. To analyze the motion, we used both a tracker video and constructed a computational model to see if we understand the motion. The results were that the predicted motion and the experimental mass's motion matched pretty well, though there were some tracker inaccuracies and air resistance that came into the play in the real system. The spring mass system, we found, does satisfy the energy principle. The main fundamental principles at play here are the energy principle and Newton's second law. Hooke's law also comes in, since we're talking about a spring. It is worth noting the relevant forms of our fundamental principles. We'll use Newton's second law in the motion predictive form shown here, and for the energy principle, we are dealing with a spring, gravity, and kinetic energy of the mass. For this experiment, our system is the spring, the mass, the connection point, and the Earth. We've intentionally chosen a multi-particulate system for reasons that you'll see later. For the experiment, we were given a video that I imported into Tracker of a mass's motion connected to a spring. We are given that this blue quantity here is 0.7 meters, a quantity collectible at the beginning of the video that you're not seeing here. As we can see when we run the video, the mass sort of follows a swinging arc. I marked the center of mass at each point, and then collected the x and y data. The data I'm highlighting right now. I later pasted this into a CSV that we will use in our model. We will use this data to compare our model to the actual experiment. Initial conditions given about the system are as follows. We have a mass of 0.402 kilograms. The ball position vector was this. We got this from Tracker, was the first point. The mass starts at rest. The delta t is 1 over 210, a very small time step for accurate predictions, and there's some math for initial conditions that I'll show on the next slide. We obtain the spring constant using an equation relating the spring constant to the omega period. This is an equation for harmonic motion in the y direction, which is what our spring is experiencing in the experiment. Here's an example. View the Wikipedia article if needed to understand this formula. We then use Hooke's law to obtain the relaxed length of the spring. Please pause the video if needed to view these equations and calculations. Here's some other initialization that needed to be done. We've already shown a lot of this in the previous slide involving Hooke's law, but these will be the actual lines of code that you will see in our model. Perhaps our most important initialization are the energies inside of our code. It is through these initializations and through these energies that we will test if the energy principle is upheld in our model. As mentioned earlier, we have a kinetic energy, a potential gravitational energy, and a spring potential energy at play in our system. K stands for the kinetic energy, UG for gravitational, and US for spring. Please pause the video if needed to see the equations that are required in order to calculate these energies. We can expect these energies to change as the mass moves. We will later graph these models to test if the energy principle is upheld in our experiment and model. Quickly going over the while loop that uses Newton's second law to check and verify the energy principle, we first update our initial energies. We then find the force of gravity, shown here. Then we also use the force, find the force of the spring. F net is simply the sum of those two. We then find the ball velocity and ball position using Newton's second law in the form shown earlier. We then update the spring and use trail dot append to draw the difference in the spring. Below that, we're updating our energies using what we just found above when we were calculating Newton's second law. Then we update arrow position for the model. Spring force will be in blue, and gravity force will be represented by a black arrow. Finally, we read in the CSV data of the tracker video that I showed earlier. We will use this to draw a red mass that we will compare to our model to see if we have a decent comparison and if model things well. Let's run this thing. You'll notice that the red ball, our experiment, matches decently well with the blue ball, our model. However, there are some inaccuracies. I may have marked things incorrectly in Tracker, and in the live experiment there may have been some air resistance. Overall, the graph on the right, which shows y position between the model and experiment, matches decently well throughout. Furthermore, modeling the x position shown here on the graph on the right, we see a sort of more consistent misrepresentation. Likely the center of mass that I selected in each frame is not the true center of mass. Still, we see very similar peaks and curves, just displaced by a little bit. We can also graph all of the energies at play in our system to see the energy principle at work. Note that yellow is the sum of all energies, blue is the change in kinetic energy, green is the gravitational potential energy, and red is the spring potential energy. As we can see by the yellow line, the sum of the energy is 0, consistent with the multi-particulate system we selected. No forces from the surroundings are transferring or taking energy out of our system. Our model system is the energy principle satisfied. Let's discuss our plot to see that. Yellow is the total energy, which we saw sat at 0. Because we chose a multi-particulate system and nothing from the surroundings added or took away energy, this shows that energy principle is satisfied. Also, energy principle states that the sum of all potential and kinetic energies is equal to the energy. Because this is how we calculated the yellow line here, we know that it's 0, we know that this is correct. Let's quickly answer the final question. Using the data from Tracker, make oscillation period estimates of x and y and compare the two. I went into Tracker and looked at the graphs produced for x and y and found the oscillation period, aka time between peaks. For x, I found it to be 1.684 seconds. For y, I found it to be 1.531 seconds. It makes sense that these values are close but not exactly the same when we look at the simple harmonic motion, aka y, and the pendulum-like motion, aka x, formulas. They're both proportional to 2 pi, but y relies on mass and spring constant, whereas x relies on length and gravity. Different values, which means that we get different sort of answers for oscillation period.